All right, my name is Logan Moore. I'm a mathematician, and my research project was on determining the surface type of a discrete Pont-Levé equation. So the first question that you're probably all asking yourselves is, what is a Pont-Levé equation? Well, generally, it's part of a much broader field of mathematics called dynamical systems research. And dynamical systems tries to study how a point moves through space given some movement equations. The big issue, though, with dynamical systems is that it's incredibly complex, to the extent that if you gave a mathematician an arbitrary differential equation, say, they wouldn't necessarily be able to solve it. So instead, we look at subsets of equations with specific properties. And the Pont-Levé equations are one such subset. Pont-Levé equations have two important characteristics. One of them is that they have 8 indeterminacies. So those are points that when you try to map them, give you an expression like 0 divided by 0 or infinity divided by infinity. So you don't know where they map. And the second property of Pont-Levé equations is called singularity confinement. And that means if you start in the defined space of your equation and eventually get onto the undefined space, you'll eventually come back into the defined space. So you can never lose track of something forever. And applications of Pont-Levé equations, the main application comes from mathematical physics. So in fact, the discrete Pont-Levé equations were first discovered in the study of quantum gravity and string theory. And for pure mathematics, their main applications are for random matrices, which are very important for math modeling. So there are two main ways to investigate a Pont-Levé equation. The first way is purely algebraically, and so that's looking at the equations themselves. Unfortunately, the equations are often quite complicated, so mathematicians came up with a second way about 20 years ago, and that's the geometric method. The geometric method started in about 2001 when a mathematician called Sakai wrote a paper showing that every Pont-Levé equation has an associated geometric surface that can describe its dynamics. And since then, a ton of work has been done on discrete Pont-Levé equations to the extent that in 2017, Kajiwara and Yamada wrote essentially a big catalog of the 22 canonical examples of theoretical equations. And then my advisor, Dr. Chimay, and I are working on a second catalog that will catalog the geometries of all of the known applied Pont-Levé equations. Because ideally, we don't want applied mathematicians to have to do all of this heavy work. We want them to have a reference. So the method that I'll be going through for this presentation has 4 main steps. The first is to locate all of the indeterminacies and do something called the blow-up procedure. We'll talk about that later. The second is to construct what's called the surface root diagram and match it to one of the known surfaces. The third is to determine how the indeterminacies evolve. And the fourth is to describe those dynamics as a symmetry on our diagram. So to start, this is my specific example. I don't put this up there so that you can memorize it. Instead, I want you to see how this is a fairly complicated mapping and why algebra might not be our best bet. And in fact, this is a relatively simple Pont-Levé equation, so it only gets worse from here. So the first step, as I said, was to compute all of the indeterminate points. I put their coordinates on the left side if you're interested, but the main thing to focus on is the diagram. As expected, there are exactly 8 indeterminacies, meaning this might be a Pont-Levé equation. And you may notice that some of them have arrows pointing to each other. They're kind of grouped up. And that's because some of these indeterminacies are actually infinitely close to each other, such that you can only find them after blowing up the first one. That's called a cascade. And for this example, we have 3 different cascades for a total of 8 points. The next step in the method is blowing up our indeterminacies. So the big issue with an indeterminacy is that once you get onto the indeterminacy, it's hard to tell where you go from there in your mapping, what the next step of the path is. So the big issue is that we lose information. However, with the blow-up procedure, we can keep that information. The general idea is you remove the single point from your surface and you replace it with an entire line. That way, depending on how you get onto the indeterminacy, you're on a different point on the line. So as you may be able to see from the diagram, I removed all of the bad points and replaced them with lines, creating a sort of cluttered structure. You may also notice that I've color coded this diagram. The red curves are called -1 curves. Those are curves where you only blow up a single point. And those are kind of tougher to work with because there can be infinitely many of those. However, the blue curves, the -2 curves, are extremely nice because there's always only finitely many of them, and they always map to each other under your dynamics. So the next step is to construct the surface root diagram. This is also called the Dinkin diagram, and it actually comes directly from the geometry. All you need to do is take each of your blue curves, each of your -2 curves, and turn those into a node and on your graph. And then nodes on your graph are connected if and only if the curves on your original diagram intersect. So this is basically a way to encode the geometry of your indeterminacies in a simple diagram. And you may also be looking at it and thinking that it's a bit skewed, but the good thing about graph theory in math is that we can actually move around the nodes as much as we want, as long as we don't cross them over each other. So you might be able to see that it's roughly a triangle. And in fact, that is a known geometry. So by referring to the big catalog by Kajiwara, Nomi, and Yamada, we can see that this Dinkin diagram corresponds to an E61 surface type. So this gives us the surface type of our Pavlov equation. However, there's one more step. Once we have the geometry, it tells us where we're working, but we also want to know how things move around. So that's something called the divisor mapping. Remember that the issue with our indeterminacies is we don't know how they move. However, when we take out the single point and replace it with an entire line, all of the points on that line are mappable. They are defined. And so by mapping those lines, we can essentially map the indeterminate points. And this is something called the divisor mapping. So I've provided the mappings specifically for the -2 curves, those nice blue curves here. And the first thing you can notice is that, as expected, they all map to each other. And the second thing is there's finitely many of them. In fact, only 7 in this example. And this encodes a lot of the information about our mapping. Essentially, it encodes the hardest part of our mapping. And the final step, and my favorite step, is taking this information, which is kind of hard to read, and turning it into a simple diagram symmetry. So in this case, all of that information we just went through is the same as a 120-degree rotation on our triangular diagram. And this is the information we want to give to applied mathematicians. So there was a lot of work and a lot of computations that I had to skim over for this presentation, but it was very labor intensive. However, the hardest parts of the computations, the indeterminacy mapping, is entirely contained within this diagram. So the point of my work is to give this diagram to applied mathematicians so they can just look at this instead of doing all of the work themselves. Thank you.
All right, so we have a few minutes, like I said, for questions. All of you in the audience, you can ask any questions about either the work or how Logan stumbled upon this or anything else that you can think of. So do we have any questions for Logan? Yeah, please.
What are the applications that applied mathematicians could use this to find out?
That's a great question. It's mostly in financial applications. So the study of random matrices has a lot to do with stock markets because we model stock markets as essentially random paths that either have like a 50% chance of going up or a 50% chance of going down. You can change those weights, but random matrices are a great way to do those computations. And so that's one of the major applications for mathematicians.
Okay, one more question. Can you get to your first slide and can I take a picture of you really quick?
Like the title? Or...
Yeah, the title slide. Okay, smile. Me being a marketing person doing my job. Thank you so much.
Yeah, well.
All right, other questions for Logan? Yeah.
What sparked your interest in this type of thing?
So I actually learned about this from my advisor. Instead of reaching out to my advisor, he reached out to me because there's a lot of computations and essentially he didn't want to do it himself. So he reached out to me, asked if I wanted to come on the project. And then, of course, over learning this project, I've grown a lot more interested in these equations as I understand what I'm actually doing now.
There's N.
You do a really nice job of explaining math to a non-math person. Thank you for that. I wonder if you could flip to slide number 10, I think it is. And you said, rather offhandedly, you can see here that they map to each other.
Mhm.
Can you show me how I can see that? I think I see matching symbology, but I just want to be
Yes.
sure that I understand.
So in particular, maybe the best way to show this is to look at F7 minus F8. That's one of our particular -2 curves. And that maps to F1 minus F2, which is one of our other -2 curves. Now, of course, I have overline bars on those. I didn't want to get into this, the specifics on the presentation, but that just means that's in the future. So these curves actually move around over time. But I simplified that for the sake of the presentation.
Thank you, very nicely done. Appreciate it.
Could you talk about how the intersecting could like lead to you actually painting an actual picture of the surface?
Yes, so the main way to look at it is through this diagram. The unfortunate thing, and the reason I don't have a great picture for everybody, is that when we do the blow procedure, when we take out a single point and replace it with a line, we actually increase the dimension of our surface each time. So by the end of this process, we have essentially a 10-dimensional surface. So it's really not easy to draw a picture except for this diagram, which gives you just the basic idea without any of the fluff. But yeah, it's a very exceptionally complicated surface.
Anyone else? No, all right, thank you so much.